All right, so at the end of class last time, we were talking about these two rings, Z mod 6 and Z mod 2 cross Z mod 3. And we were trying to decide if they were isomorphic to one another. And so what do we mean by isomorphic? So isomorphic means that not only do they have the same size, okay, something to think about. So, but also can we make a mapping between the two that preserves addition and multiplication, okay? And so, so that was our challenge, was to think about how can we map, either mapping things from here to over here or vice versa. So we could kind of think of our mapping either way, and write down what that is. Okay, so thoughts? Well, let's start with what we know has to map somewhere, right? And then kind of go from there. So what do you think has to go? Yeah, so the 0 element here has to, so let's say we have let's define a function f from, let's see, f colon Z mod 6 to Z mod 2 cross Z mod 3. And instead of writing out my function, let's see if we can think about what needs to go where. And then, so that goes to, okay, so really, I'm going to write it this way. Right, so I could drop the brackets. Is it okay if I drop the brackets? I think this is what we mean. We mean the congruence class of 0 here. And we mean this is the congruence class of 0 in Z mod 2, and this is the congruence class of 0 in Z mod 3. Okay, so that's what we mean. I'm going to drop the brackets just because they're a little tedious to write. But just understand that this 0 is not just a 0, it's a congruence class. Okay. Why am I not using this? I don't know. Okay, so 0 goes to 0, 0, right? And then you were thinking that 1 needs to go to 1, 1.
I didn't say that, but I was just saying that
the 1 over here needs to go to the 1 over here.
Yeah.
Right? Okay. So what is the 1 over here?
But for a second, I think it sounded reasonable that it might be 1, 1.
That it might be 1, 1. Yeah, because when I think about that, I kind of gave that away. I just could have asked you all that. but if I think about it, if I have some AB and I multiply it by 1, 1, right? Then that's going to give me AB. A times 1, B times 1. Right? And since we have commutativity here, it's going to work the other way too. So 1, 1 is going to be my 1 element there. And then if I wanted to preserve multiplication and addition, I can start thinking about what needs to happen here, right? So from this, we ought to be able to figure out what the rest of the things map to. So we can either do that by thinking about addition and multiplication tables, or we can kind of think about what this mapping needs to, what needs to happen here, or I don't know, any thoughts or ideas? What do you think 2 would map to?
Maybe 1, 2.
Okay, why?
Because or 2, 1, 2, 2, 3. Or sorry, maybe 0, 2.
0, 2?
There's
Mhm.
n Z mod 2.
Mm-hmm.
It'd be 0, and then n Z mod 3. 2.
Okay, so you're thinking about taking this and taking it like mod 2 and mod 3 as your kind of your mapping. Yeah. Well, so I know that this 2 over here is equal to 1 plus 1, right? Is what this 2 is here. Yeah. So if I did that, if this maps to 1 and I want to do that, this 1 plus 1 needs to equal that. Does that work? So if I do 1 plus 1, I'm going to get 2 comma 2, but then I need to do that mod 2 and mod 3. So I'll get 0, 2. Does that sort of make sense? And then what would 3 go to, you think? 1, 0. Because it would go to 3, 3, kind of 3, 3, and then you would do it now. And then 4 would go to, and 5, 1, 2. And that's it, right? The 6 elements, mapping to 6 other elements. Okay. And so this would be our mapping. Now we need to prove some things about this mapping. And I haven't written down, have I written down the definition yet of an isomorphism? I think I just kind of, did I write it down? That it has to satisfy. No, I just kind of wrote down like a general idea of what an isomorphism
Yeah,
is.
we wrote have the same.
Have the same structure. Okay, so let me define what we mean by an isomorphism, and that way we will have some properties that we can check to see if this mapping is in fact an isomorphism. Okay, so here's the definition. So the way that they define this in the textbook is kind of interesting to me because it was kind of backwards of the way I think about it. But maybe it's a little bit more intuitive because you want to kind of figure out like, how do I say that 2 rings are essentially the same, right? Well, I would need to prove that there is an isomorphism. But I just want to point out, we're about to define something called a homomorphism. And a homomorphism is a mapping that has those properties. So we'll just kind of note a homomorphism, which we'll define in a little bit, is a mapping between rings with these properties. So the way that I think about this is I think about homomorphisms first, and then I think about an isomorphism as a bijective homomorphism. Anyway, this book kind of does it backwards. And I think the reason is because they're kind of motivating it by like, how can we tell if rings are the same? And then kind of going through the isomorphism first. But yeah.
Are little a and little b like elements of R or?
Yeah, so yeah, that's a really good question. So the little a and little b are elements of R. Okay, so yeah, so let me point this out. So these guys are elements of R. Okay, and then these guys here are elements of S, okay? So those guys are elements of S. And this is multiplication in S. And this is addition in S. Okay, and this inside of here is multiplication in R, right? And then this is addition in R. So on this side, like inside the here, we're doing addition and multiplication in R on elements of R. And when we go to the other side, we're talking about elements of S and addition and multiplication in S, right? So So I think that's a really good point to think about because it may seem like we didn't do anything, you know, a little bit. But we'll have we'll do a lot of examples and non-examples of homomorphisms. And so you'll start to kind of get a feel for like what types of functions have this property and what types of functions don't, right? So we'll talk about that a little bit more. Let's think about the mapping that we had here. Is it injective and surjective? So to be injective, what has to happen? Do you remember? Injective is 1-to-1. Yeah, that. Was that what you were going to say? So what does that mean? Yeah, right. So distinct elements get mapped to distinct elements. Is that happening here in this? Yeah. And surjective says what? Yeah, so everything over here is hit by something over there, right? So every element in Z12 cross Z13, is this all the elements in Z12 cross Z13? You have a feel for that? How many should there be? 6, right? 2 times 3. So we should have 6 elements. And they're all distinct here. And they all get hit by something there. So I have a bijection here that I've written down. Okay. And then the question is, does it satisfy this homomorphism property? So to check that, I would need a way to write the function down that's different from just this table kind of way, right? And so what Julie suggested is exactly the right mapping. So we can say F takes some element in Z mod 6 and maps it to, you take that element in Z mod 6 mod 2, comma, and then that element in Z mod 6 mod 3. All right, so that's the mapping that we did. So I just want to point out the little difference in the arrows, right? So you see this, oh, actually I can write actually an equal sign here. So let's write an equal sign here. That's better notation. So F of A equals that. And then here, this is showing a distinct element, and this is a mapping to that element, right? And then this arrow without the little bar is showing between the rings for mapping. So that's kind of the notation that we use. So there's my mapping. So does it have those homomorphism properties? Let's check. So if I did F of A plus B, well, what does that equal? Well, that equals, I'm going to do A plus B mod 2. And then I'm going to do A plus B mod 3. Okay. And then how does that break up? Is A plus B mod 2, is that equal to A mod 2 plus B mod 2? It is, comma, and then A mod 3 plus B mod 3, right? And then how does it break up even further? Now I can break it into 2 things added up, right? So I can do A mod 2, B mod 2. This dang crap here. B mod 3. And then, oh, no, wait, yes, no. I want to do this. AA plus B, right? And what is this? How can I rewrite that? That's F of A. Right? That's F of A. Plus, now the addition in Z mod 2 cross Z mod 3 is this addition of, it's this special addition. It's almost like vector or, coordinate addition, right? It's kind of what we've got there. So this is equal to F of A plus, with the plus over here, F of B. So I've shown that it works for the addition case. I've shown the homomorphism works. Okay, and you did a similar thing for multiplication. It's going to work out. Okay. So, yeah, so that's what we're going to do. So the whole rest of this chapter is just exploring homomorphisms and isomorphisms. Okay, so that's all we're going to do over and over. So, let's do a million examples. Oh, and Julie, I was gonna tell you, I was looking through the textbook for problems that I didn't assign for, that I had, we could use for examples, and take a look at this. And, let me write, I can do that, let's do this example, because we dealt with it, yesterday, but I say yesterday, I mean last time, you know what I mean? Okay, so, 1.3, number 18 in the textbook. So this is not an assigned one. It says, show that the isomorphism of Z mod 5 and that set 0, 2, 4, 6, 8 in Z mod 10 is given by the function whose rule is Can you write it down? Do you remember what your rule was you came up with? Let's see if you can write it down without the.
The multiplication of 6.
Yeah. So you take something over here. So we'll write it this way. Right? Equals. So we do 6x, but we take that mod 10. Right? And so that was the mapping you were describing. Right? So this function goes from, I'll write it above because we usually write this goes from Z mod 5 to this set 0, 1, or 0, 2, 4, 6, 8, right? Okay. And Colin was describing a map that went the other way. Right? And what was your mapping?
I think it was. It was modulo 5. Wasn't it?
Yeah, so you're just taking whatever it is in mod 10 and just taking it mod 5. Yeah, so that gives you x mod 5. So 6 goes to 1, right? 8 goes to 3, 4 goes to 4, 2 goes to 2. That was the mapping we had done earlier. Yeah, so this is a mapping going the other direction. And in fact, we can prove that they're both, well, I mean, we showed that they're both isomorphisms really, but you can go back and forth between them. So, so this ends up being an inverse map of that map. Yeah.
If isomorphism, as opposed to homomorphism, isomorphism requires it to be bijective. Does that mean it's isomorphic both directions? The inverse function would also work?
Yes. It's not always easy to write down what the inverse map is, though, depending on what the mapping is, right? But yeah, so you have to have the mapping going back and forth, and because they're essentially the same, right? The same ring. It's kind of the idea, structurally the same. Yeah. Okay, but yeah, I was looking through and I saw that and I was like, hey, that's Julie's map. So kind of fun. Yeah. Okay, cool. So yeah, so let's do some other examples. And let me move my iPad over here. I'll forget that if I leave that there. Okay. So let's let K do this. So K is going to be the set of all matrices A, B minus BA with that structure. And we're saying the complex plane, which is the set of complex numbers, A plus BI, such that A and B are in R. So we're going to look at those two. So let's define F from K, oops, okay, I'm so used to writing an R, so from K to C. Can you guess? F of A, B, negative B, A maps to, well, equals. What do you think? Just guess.
A plus B.
A plus B, yeah. That's enough. Okay, so here's the question. Is F an isomorphism? Okay, so we have to check. Well, what do you want to start with? We could start anywhere. Is it going to be injective, surjective, and have those homomorphism properties? When you're doing this and we're asking to show, is it a isomorphism, you want to kind of think about where might this break down? You know, where might this break down? Or maybe it is a isomorphism, I don't know. So you want to just start, try some things? Okay. You want to do the homomorphism properties first? Or maybe the injective, surjective you haven't done in a while, so. You'd rather start there? Yeah. What do you think?
I hope this isn't completely random since I guess we're not quite on homomorphisms yet, but if homomorphism doesn't require the map to be bijective, does that mean it's directional? Like, okay, so would you say, so like, okay.
Yeah. Okay, so let's solution. Okay, so let's start with injective and surjective. So do you want to do the injective bit first? So for injective, where do we start with for an injective? We want to start with two things here being equal to one another and try to show that the things you started with were equal to one another. Okay, so we're going to assume that F of A, B, negative B, A equals F of C, D, negative D, C. Okay, and then our goal is to prove, well, essentially we're going to prove that A equals C and B equals D is what our goal is. If we could do that, then that would show that A plus BI is equal to C plus DI. So, so what is that? That's telling me, so if those things are equal there, that means that A plus BI equals C plus DI. And what does that give me? Well, the real part has to equal the real part and the complex part has to equal the complex parts, right? So A equals C and B equals D. And what does that tell me? That tells me that the thing over here in K, these matrices, so A, B, negative B, A is equal to C, D, negative B, C. So I started with that the images were equal, and I came to conclude that the things that we were mapping were equal. Okay, so that's injective. What about surjective? We're going to choose something in here, right? So we're going to choose A plus BI in C. And now I have to find something that maps to that. Well, you know what I'm going to do? I'm going to use different letters than A and B because I want it to be clear that we're picking a specific one. So I'm just going to say, let's just do like U plus BI or something. So I'm just going to pick something over in that complex plane. I don't want it to seem like magic, right? So what is going to map to U plus BI?
UV minus UV.
Exactly.
Wait, UV minus VU.
That one. Yep. So then we were going to say consider So we have a feeling for what it's gonna be. So we're gonna consider u v minus v u. And then I can say f of u v minus v u equals u plus vi. I keep wanting to make the I a subscript for some reason, vi. And so by our definition, so I've chosen something over here and I found something that maps to it. So it's surjective. So there's not a lot to do here because it just kind of falls out from the definition of the mapping. So it's surjective. I cannot spell. Okay. Y'all probably already needed that, so. No spell check on a whiteboard, so it's hard. Okay, so it's injective, it's surjective, this is looking promising, right? Let's see if it satisfies those homomorphism things. What if I do, okay, now what do I need to think about? I wanna do, this is gonna be, I'm gonna take two things in K. So that's two matrices, right? And I'm gonna be adding those with matrix addition, right? Inside of that F. Okay, so let's say F of, let's put up my two matrices. So we'll say A, B minus BA plus C, D minus DC equals. Okay, so I can add, I can go ahead and add them inside of here, right? So that is F of A plus C, B plus D, negative B minus D, A plus C. Okay, and so then I'm gonna do the mapping. So what does my mapping do?
A plus C plus B plus
A plus C plus, I'm gonna put in parentheses here. B plus D. I. Okay. Then what? Follow your nose. Distribute the I, yeah. So we'll have A plus C plus BI plus DI. Then we can gather the terms we want to gather here. So this is going to be A plus BI plus C plus DI. And what is A plus BI?
F of A.
Plus F of C. You see how these proofs work? And the multiplication will be a little different because I'm gonna have to do matrix multiplication inside here, right? So remember that? We're getting a refresher on that, aren't we? Okay, so we have, yeah, and I'm always confused about, do I do a double parentheses here? Like these parentheses are for the function and those are because of the matrix. I don't know. Yeah, you can kind of. As I was writing this, I was like, maybe I should be making double. Okay, A, B, C minus B, C minus B, gracious, minus B, A multiplied by C, D minus D, C. This is where I'm feeling like things might break down because matrix multiplication is a little weird, you know, but maybe it'll be okay. I'm not sure. I actually didn't work this one out yet, so I don't know. So we'll see. Okay, so let's do our matrix multiplication. So remember, we go AC minus BD, AD plus BC. Then we'll get negative BC minus AD. Hey, it might work. And then we're going to get minus DB plus AC. Is that of the form we want? Oh, we need F of that. Okay, F of that. Well, we've got these two guys are the same, right? And then that's the minus of that. So we're good. Okay, so then let's see what that maps to. Well, that's going to map to this plus I times that, right? So AC minus BD plus I times AD plus BC. Okay, and then where are we trying to go here?
It's A plus BI times C plus B.
Yeah, we might need to do scratch work for that, because I'm not sure. So what is A plus BI multiplied by C plus BI? Is this gonna give me what I want? Okay, so I'm gonna get AC plus ADI plus BCI plus BDI squared, which is negative BD. Yeah, because I squared is -1. So minus BD. Is that what I want? Is that what I got? Yeah, I've got all that. I got AC, I got negative BD, I got ADI, and I have BCI. Yeah, so I'm gonna do this dot, 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 and then that gives us what we want. A plus BI, C plus BI. For my scratch book. Okay, and then that's F of this. That's F of that matrix times F of that matrix. So it is in fact an isomorphism. Yeah, Colin?
Multiplication on complex numbers is commutative, so do we have to do it again with the matrices the other way? Or do we want to? I mean, like,
You're saying, so matrix multiplication is not commutative.
yeah, so, but if it's an isomorphism, then if you switch the matrices, it's the same as switching the complex numbers, which shouldn't change the answer.
Right. Yeah, and I think that's a good question. I think what will happen is if you change the orders, it'll change the orders inside here, but you'll get the same, like, because it's commutative inside the real numbers, inside these entries. What if you, okay, hang on, I'm actually not sure, that's my theory. So if we did CD negative DC, these are good questions to think about. AB minus BA, what does that give me? That gives me AC or CA minus DB, right? CB plus DA, negative DA minus CB, and negative BD plus AC, CA. Gosh, okay. So that's the same as when I multiplied. You know what I'm saying?
Right.
It's only different because like the ordering is different here. Well, I kind of messed up, but anyway, the ordering is different here, but since it's commutative, well, since we're in the real numbers in these entries, this is the same as that. Right.
Right.
So so even though matrix multiplication is not commutative, it works out in this case. But that's a good thing to think about because you want to think about you know, since this is a multiplication in R and this is multiplication in S, we want to make sure that it works out. So I think that what's happening is because of the way that these are structured in K.
You get A twice. And like
Yes,
B.
I think that this subring is commutative. That's my suspicion.
Yeah.
I think we just proved it, that subring is commutative. Even though matrix multiplication in general is not commutative, it's commutative here.
Oh, so
Well, it has to be because it's isomorphic to a commutative ring, right?
yeah, I was
We
gonna
just
say, so that means since it's a bijection, if you prove something about, well, I guess, okay, maybe not anything, but like, so commutativity, and then you prove isomorphism, that means the other thing is commutative.
It has to be, yeah. Although, you know, there's probably a theorem, we'll probably need to prove that, but yes, that's the way it's gonna work out.
Okay.
Yeah. And speaking of theorems, we have like a whole bunch of theorems stacked up that we need to prove. So we've been playing around a lot and we haven't really proved anything. So we need to prove a whole bunch of theorems. But let's not do that today. Let's save the boring theorems for Monday. For today, let's finish a bunch of examples. So I think the examples will help you on your homework. The theorems you can look up in the book if you need them. But we'll spend some time proving theorems on Monday. And then that will be kind of the end of chapter 3. We'll finish that up on Monday. I was trying to finish it today, but that's not gonna happen. Okay, so let's look at this one. Maybe I'll leave the definition there. What if we map? What if we view F from C to C? And we're going to define it as F of A plus BI equals F of A minus BI. Is that an isomorphism? So you're mapping each element to its conjugate, complex conjugate. Okay. Which parts of this do you want to start on? Yeah, Seth.
Just kind of off topic, is the next exam only over chapter 3?
Oh, yeah, and I have a list of definitions to give you, definitions and theorems. Because I've started making a draft of exam 3. So I have a rough idea of the kinds of things I want you all to do. There's not like a big, it's really the second exam, we didn't have like a big theorem, you know? But like any of these theorems you should be able to prove, because the proofs are pretty short and pretty straightforward. There are some like funny things where you have to like add 0 in a creative way or multiply by 1 in a creative way. So there's a few little tricks and things in some of these proofs, but overall, there's not like a main one, like a big thing I want you to memorize. But yeah, so I'll let me write that on my hand. So for the definitions, I'll send that out today. I'll put that up on Canvas. Okay. Yeah, and some of the theorems we haven't proved yet, because I've been kind of stacking up a bunch of proofs to do all at once. Okay, so is it an isomorphism? What do you think? Do you have a gut feeling? Maybe not yet. You haven't done enough to develop a gut feeling.
I have a question.
Yeah, sure.
Whenever we are mapping from like one set to itself, like we're doing here with the C and C, whenever we're thinking about injective and subjective, how do we think of what is, because like, at least how I've always understood them is like going from one set back to the other, but now we're all in the same set and I don't really understand how that would work.
Yeah. Yeah, well, let's do the injective subjective part of this, right? Well, let's do it. Okay, so here's our proof. Well, we didn't decide if it's yes or no yet, but anyway, so let's do the injective. Okay, so Brandon, walk me through what we need to do. I need to take something where? The domain or codomain? I need to start by,
You start with the
I need to start with the images of two things in the codomain that are equal, right? So I need to say, I need to assume that these two images are equal. F of A plus BI is equal to F of C plus BI. And then my goal is to prove what?
A plus B I and C plus C, or C plus B I.
Right. Right.
Where, this might sound like silly, but where are they? Are they also in C? Or
They
no?
are.
Okay.
Yeah. So A plus BI are in C. A plus BI are over here. Right. These are inside the function, so they're over here.
Okay.
Right. But this whole thing is over here.
Is that not the same set?
It is the same thing.
Okay.
Yeah.
So why
So go ahead.
we're mapping the function to the function. There's not just like, because the other one we had just a complex number that was mapped.
I'm not sure I understand your question. Maybe you haven't formulated it.
Yeah,
Oh, wait, would it make more sense to say F of A plus BI equals just A minus BI without the F.
Oh,
That's why I'm getting confused, because they're both F of,
yeah, yes, okay. That's what I meant to write.
Okay, that makes a lot more sense.
I did not see that, y'all. I'm so sorry. No wonder everyone's flipping out. Okay, that's what I meant. My mapping is just mapping an element in C to its complex conjugate, also
Gotcha.
in C.
Okay.
Okay? Okay. Thank you. Yes. That was embarrassing. Okay, that's fine. It's all good. So, so what is f of a plus bi equal to? Now you're gonna fly through this.
A
This
minus
is gonna be
bi.
easy. Okay. This is a minus bi, yeah. Yeah, I was kind of like, why is this so hard? It should be easy. Okay, and then this is c minus di. And so what does that tell us?
it's A is equal to C.
That's a equals c, and negative b equals negative d, which implies that b equals d, which implies that. Yeah. Okay, so it's injective. What about surjective? So we need to choose something where? Domain or codomain? I'm missing a lot of people. Someone's online. Who's online? It's online. Yeah, and the codomain. So we're gonna pick something over here. So we're just gonna call it, so let's say choose. And I'm gonna use some different letters just so that it's, you know, it doesn't seem like we're just writing down what the map says, right? So let's choose some like U plus BI and C. And then what's gonna map to that U plus BI? You think?
Should it be minus BI?
Yeah, so we're just picking an arbitrary element in C, right?
Okay,
Yeah, and then what element in this C is gonna map to this element in this C?
U minus BI.
U minus BI, right? Yeah, so then we'll have consider U minus BI in C. And we'll say F of U minus BI is equal to F, or is equal, no, I did it again, okay. Is equal to U minus negative BI is equal to U plus BI. So I've landed on the one I chose to begin with, right? So I picked the thing that's lands on, yeah.
Could you do it the other way? So could you say that U minus VI is in C and then consider?
Yeah, you
Yeah,
could,
okay.
except like if I told you to choose an arbitrary element of C, you
Uh-huh.
would always just use a plus.
Okay.
You know what I mean?
Okay,
So, you could,
Okay.
you could, and that would make sense in this case, but I think usually if someone's just taking an arbitrary element of C, you would usually use a plus sign and just to know that that B could be negative, you know? So, but I understand why that feels a little backwards to y'all. Okay, so there we go. So it's surjective. And it's actually gonna, the homomorphism stuff is all gonna work out too. So I'm gonna move on to a different example, just so I can get a whole bunch of examples in today. Okay, so what about these two kind of special maps? We'll call this the I now, and it's like an I without a dot. I think it's an iota. I think it's a lowercase iota. It looks like a little I without a dot. So I always try to dot it. But anyway. Okay, we're gonna go from R to R. So just a ring to a ring. So from a ring to itself. And we're gonna say I of R equals R. So how would you describe this map?
Idempotency.
Yeah, so this, we actually are gonna call this the identity map. And so, because it maps every element to itself. Okay, now you've seen this in the real numbers. What's this map in the real numbers? Yeah, in the real numbers. So if you look at f from R to R, and you do f of x equals x, that is our identity map that maps every element to itself, right? So we're familiar with this mapping, but this is the identity map for just any general ring, maps every element to itself. And so is it going to be an isomorphism? Will it be injective? Yeah, you can't map, if you're mapping just an element to itself, it's not going to end up being some other element, right? So it's going to be injective. Is it going to be surjective? Well, everything over here, I can plug it into this map and get something, so it's going to be surjective. Is it going to satisfy these homomorphism conditions? It is, yeah. So this is an isomorphism. We call this the identity map. And I want to think about that name for a minute, right? We've talked about identities before, haven't we? When we talk about an identity element, what kinds of identities have we seen? An additive identity and a multiplicative identity, right? And so then we're also calling an identity. And so I was talking about before that when we say something is an identity, we're asking with respect to what operation, right? And so we have an identity with respect to addition. We have an identity with respect to multiplication. And so my question to you is, if I'm calling this an identity map, it's an identity map with respect to what operation? What do you think, Colin?
Would it be functions?
Yeah, yes, it would be functions, but what operations do we have on functions? We'll talk about this more in chapter 4. Because chapter 4, we'll talk about polynomial rings. So what do you know about operations on functions that we have? Can we add functions? Function addition?
Yeah.
Yeah. Function multiplication? We can multiply functions? Yeah.
Maybe composition.
There's
So
function
like,
composition, right? Function composition. Do you remember when we talked about inverse functions in algebra? And how did you show that a function was an inverse function of another function? You composed it with itself. And if you got this map, it was an inverse, right? And so this is going to be the identity map with respect to function composition. We can explore that some more later, but I just wanted to plant that seed. So that's going to be the identity element with respect to function composition if we had a ring of mappings. So you're kind of getting a little meta here, right? So you think about numbers, and then I could do mappings between sets of numbers. I could do mappings between sets of matrices, right? But then I could do mappings between sets of mappings, right? And so that's what we're going to do when we talk about polynomial rings. We're going to be talking about rings of polynomials, those are mappings from real numbers to real numbers. So it starts to get like, you have these layers, which is kind of fun. One more map. This is a boring one. Do we have a name? Well, does the book have notations on this mapping? Okay, they're using Z. So if we do Z from R to R, given by Z of R equals 0R. What kind of map do you think this is? We call this the zero map. Everything maps to 0. And this map is also an identity with respect to what operation on functions?
Be the inverse.
So this is the identity with respect to function addition, right? So this is going to be the identity element with respect to function addition. that's gonna be the identity with respect to function addition. So if you add the 0 map to another map, it doesn't change that map, right? Because everything, it's gonna take everything to 0, so. Okay, so that was all I had for today. So, I didn't define homomorphism, but really homomorphism is just these, it has these two properties, like that's the definition of homomorphism. So I got close to the end. So on Monday, we'll prove a bunch of theorems and do some more examples, and then we'll be done with chapter 3.
And
Thank you.